Hello friends, I welcome you in lecture number 46 on Laplace transform. In this lecture we are going to discuss about unit step function, which is also known as Heaviside's function. So first we understand the definition of unit step function. So suppose I consider any non-negative real number, say a, and suppose our function is defined in this way. Suppose we denote our function by f of t. So for this fixed non-negative real number a, we define our function in this way. If value of t is less than a, f of t is 0, and if t is greater than or equal to a, value of function is 1. So if we understand graphically, then suppose I consider values of t on x-axis and values of f of t on y-axis, and a is a non-negative real number. So suppose a is somewhere here and this is 0, and suppose this much distance is 1, then if t is less than a, value of function f is 0. So graph of function is on real axis or x-axis if t is less than a, and for t greater than or equal to a, function has value 1. So graph of function will look like this. So this function depends on this non-negative real number a. For every non-negative real number we can define this type of function. Suppose we consider a equal to 2, then here we will consider a equal to 2. So our function will be equal to 0 if t is less than 2, and it is 1 if t is greater than or equal to 2. So because this definition depends on this non-negative real number a, the notation for this function is u of t minus a, or some other authors use this notation also. It is a function of t and is defined corresponding to this non-negative real number a. So these are the different notations. This function is known as unit step function. Another name is Heaviside's function. So sometimes it is denoted by capital H of t minus a also. So this is the way how unit step function is defined. So they can ask you to define unit step function, and you should remember definition in this way. For a non-negative or for a greater than or equal to 0, unit step function is denoted by u of t minus a or capital H of t minus a or u suffix a of t, and is defined as u of t minus a equal to 0 if t is less than a, and 1 if t is greater than or equal to a. The unit step function is also known as Heaviside's function. This is another name for unit step function. Now this definition depends on this value of a. Suppose we consider a equal to 0, then our unit step function becomes u of t equal to 0 if t is less than 0, and 1 if t is greater than or equal to 0. And here these are the graphs of unit step function. This is for arbitrary value of non-negative real number a, and this is for a equal to 0. So here up to 0, graph is on x-axis, and 0 onwards value of function is 1. So graph is going in this way, and here it is 0 if t is less than a, and 1 if t is greater than a. So this is the definition of unit step function. It is defined for particular value of non-negative real number a, and if t is less than a, value is 0. If t is greater than or equal to a, value of unit step function is 1. Now we prove that Laplace transform of unit step function is e raised to minus a into s divided by s, where s is positive. So we try to prove this formula by the definition of Laplace transform. Before that, we just write down the definition of unit step function. U of t minus a has values 0 and 1. Value of function is 0 if t is less than a, and 1 if t is greater than or equal to a. Now, by the definition of Laplace transform, we can write Laplace transform of unit step function. By definition of Laplace transform, Laplace transform of unit step function u of t minus a equal to improper integral 0 to infinity e raised to minus st multiplied with u of t minus a integral with respect to t. So this is the definition of Laplace transform. Now integral has limits from 0 to infinity, and we can write integral from 0 to infinity as addition of two integrals, integral from 0 to a and integral from a to infinity, because our function this u of t minus a has different values for 0 to a and a to infinity. So first we break this integral into two sub integrals, 0 to a e raised to minus st u of t minus a dt plus integral from a to infinity e raised to minus st u of t minus a integral with respect to t. Now in 0 to a, value of t is less than a, therefore value of this unit step function is 0. So this integral becomes 0, and for t greater than a, value of unit step function is 1. Therefore we have integral from a to infinity e raised to minus st integral with respect to t, and this we can simplify. Integral of e raised to minus st is e raised to minus st divided by minus s. Here integral is with respect to t, therefore variable s is considered as constant. Limits of integration are from t equal to a to infinity, and first we consider t tending to infinity. So for t tending to infinity, we can write in this way: minus 1 by s is there, and we can write one more step. We take minus 1 by s outside, and we have limits from t equal to a to infinity. Minus 1 by s is independent of t, therefore we can take it outside. Now this is equal to minus 1 by s, upper limit is t equal to infinity. That means we are interested in the limit of e raised to minus s into t as t tending to infinity, minus lower limit is t equal to a, that is e raised to minus a into s. Now if we take t tending to infinity, we have this type of situation, minus s into infinity, and if s is positive, s into infinity will be equal to infinity, and this is e raised to infinity, and e raised to infinity is infinity, so this is 0 provided s is positive. If s is negative, then we will have e raised to infinity here, and we will get the divergence, but we are interested in the value of s for which improper integral is convergent. So we consider s positive so that this limit becomes 0. If s is positive, then s into infinity is infinity, and due to this negative sign we have e raised to minus infinity. So if s is positive, this term becomes 0, and we can write this as minus 1 by s 0 minus e raised to minus as, and here we mention in the bracket that for s positive. Now this is e raised to minus as divided by s whenever s is positive. If s is negative, Laplace transform does not exist. Therefore, we have proved that Laplace transform of unit step function u of t minus a equal to e raised to minus a into s divided by s, provided s is positive. And we will remember this formula for the Laplace transform of unit step function. So remember this formula, and if I have a equal to 0, I will have Laplace transform of u of t equal to 1 by s, provided s is positive. So this is particularly when a equal to 0. So in this session we have defined unit step function, and we have obtained the formula for the Laplace transform of unit step function u of t minus a, and the formula is e raised to minus as divided by s, provided s is positive. So this is all about this session. I hope you like it. Thank you very much.